Can we do a quick example of that?
Vectors, yes. So just think of like a 2D vector. This is usual formula for length of the hypotenuse.
So if the vector was 2 comma 4, you would just do 2
Yes, it will be square root of 2 square plus 4 square.
and then square root of that. Okay.
Yes. The
And
idea is that you can extend that for any dimension. You just add up all the sum of squares.
the sum of squares. Yes. Okay. Got it.
Okay.
Perfect.
And the second thing is slightly more tricky to give an intuition, but the idea is that x dot y, if x and y are pointing to the same direction, then x dot y, the dot product should be square of this whole thing. So x square times x square. Because theta angle should be 0, so cos theta will be 1.
Yes.
And on the other hand, if the vectors are like perpendicular to each other, so theta is 90 degree, so then cos theta will be 0.
Wait, but
So then
if it's the same vector, the angle
the
between
angle is 0.
is 0.
Yes. So the cos theta will be 1.
So the dot product, okay. So the dot product will just be x squared then, the magnitude of x squared. Yes. Okay, I'm with you. I'm with you. Yes.
Yes. And then we say that two vectors is orthogonal if
How do
x
you
dot y
find
is.
the angle between two vectors? Wait, what?
What you do is basically you calculate x dot y by the earliest formula, and you separately calculate absolute value of x and absolute value, like the length of x and length of y,
And
and
then
then solve this equation to get the theta.
okay, yes, got it.
Okay.
Perfect.
So you can write it like cos inverse of x dot y divided by
Oh, you'd have to do
length of x, length of
oh
y.
gosh, yeah, you'd have to I forgot about that. Yeah.
Yeah. So that's the formula you'll see in a lot of things.
You're not just dividing. Yeah, you have to do cos inverse. Okay, yes.
Yes. So that's basically the idea. But like the cos inverse itself is like not very important. Like you should think of vectors in the sense that they're pointing in same direction, then the angle is 0. And if they're orthogonal, then the angle is 90 degree, means the dot product will be 0.
Yes. Because the cos theta would be 0 then.
Yeah, cos theta is. Okay.
Yeah.
So by just looking at like if the vectors are of unit length, like the length are all both 1, then just looking at x dot y tells you like whether they are in same direction or not.
Whether they're what? Sorry?
Whether they are in the same direction or like how
Yes.
similar they are.
Yes.
So this
The
is
dot
kind of a similarity metric, people say.
that makes sense. The dot product can tell you that then as well too.
Yes. Now, the similarity metric that we discussed, now suppose we are doing some regression and you're doing feature analysis. Like you have, say, 1,000 features,
Okay.
but I want to drop some features which are very similar to each other.
Okay.
So I will represent each feature as a vector, and then I will measure the angle between the vectors. And if, say, the angle is less than 5 degrees, I will drop one of them.
No way. That's so cool. Okay.
Okay.
That's why, okay, that's then feature selection, everything else.
Yeah, that is like the very basic rudimentary feature selection that you can do.
Why
If
though?
the angle is very
So
small,
similar,
then these two features are similar to each other, then I'll drop one of them.
then you drop it. That makes sense.
Yes.
But if they're
Uh,
orthogonal, then they're very different. So you want to
they
keep
are very different, so you should keep both of them.
got it. Got it. That's cool,
Okay. So
Sujay.
if you
Okay.
want to have features which are as orthogonal as possible to each other, then your regression works well. And if you have features
Great.
which are very
Okay,
similar to each
so
other, you drop one of them.
you
So
know
like this is I have done practically this a lot of times.
you know what's
If you
crazy?
have too many features, drop some of them just by looking at the angles between them.
This is the first time linear algebra I've found use for it.
Okay.
I guess
Okay,
physics.
that's it.
Physics was there.
Yeah, yeah, physics definitely you have
Was
used
good.
vectors and stuff, but like
Amazing.
that's a different kind of thinking.
Yes. Okay.
Statisticians' way of thinking is a bit different.
This makes sense. And then you've written orthogonality means the dot product is equal to 0. That
Yes.
makes sense. Perfect. Okay.
So that's mostly it about vectors. So I'll move on to slightly other things
Okay.
like linear functions and matrices and
What
stuff.
is the difference between, wait, maybe you're going to get into it, but I know
Yeah.
there's also the other word cross product, but that's not,
I won't discuss cross product at all. So cross product is something people do only in 3 dimensions. There is no cross product in dimensions other than 3.
oh, okay.
This is like a deep result in mathematics that the cross product only works in 3 dimension. And it happens that we are living in 3 dimensions, so people do physics cross product a lot. But outside of that, there is no use.
So I don't really need to have that.
For our purposes, so we don't need a cross product.
Got it. Okay, cool.
There is something called a wedge product, which is a generalization of cross product, which is something people in maths do a lot, but not very relevant for us.
What is that word? Wedge?
Wedge, yeah, wedge. So you are crossing. So generalization of crossing is creating some wedges
Got
here
it.
and there. So we'll create a lot of angles and stuff.
Got it. Okay.
Okay. So let's move on to linear function now. So basically we have a vector space. Let's call it V. And then I want to consider functions f from V to real numbers, which are linear.
Okay.
Okay. Now suppose the vector space is 2 dimensional. So that means this is as good as doing function of f of x comma y.
Agree.
Slightly more mathematical notation to this. F of the x comma y vector.
Okay. Yes.
Make sense?
That's one input.
This,
You're not having two.
yeah, x and y together is one input.
Yes.
Okay. And then we know this is linear, so it has to be something like ax plus by.
Yes.
Right? Now ax plus by we know can be written as dot product of a comma b vector and x comma y vector. Agreed?
God. Can you wait? Don't tell me. Can you scroll up for 1 second to the dot product?
Yes. Yes. This is the definition.
Yes, that makes sense then. Yes, perfect.
Makes sense?
Yes.
So then if we write x comma y is a vector v, so what this is doing is f of v is a comma v vector. Sorry about that. This dot v. Right?
Okay.
I'm just writing x comma. So that means this linear function, what it is doing is it is looking at the input and doing dot product with something, a comma v vector.
Yes.
So
That's
just
the
by
same thing we described in the beginning, though, with the A matrix, right? The capital A matrix.
yeah. So I haven't done the matrix stuff yet. So we'll do the matrix stuff later on.
Okay.
But this is basically the same thing with a scalar output.
Yes.
Matrix gives a vector output. This is the scalar output.
Got it.
Okay. So what I'm saying is the function f is same as the vector a comma b. They are doing the same work. The function takes in the
Yes.
input v,
Because that's
and the vector takes in the
manipulating the vector then. Yes.
yeah, manipulating the vector.
Okay.
So linear functions are also vectors.
Linear functions are also vectors. I agree.
Okay.
Yeah.
Okay. Now it is a bit different than ordinary vectors in the sense that you have to do a dot product. It's not that you can multiply the vector with the vector.
Yes.
Okay.
Yes.
So there are multiple ways of like thinking about this. One is that people like in our textbooks and all, we used to think of row vectors and column vectors.
And column vectors.
Okay? It's just a notation whether you write the vector as a row 1, 2, 3, or you write as a column
Yes.
1, 2, 1, 2, 3. Okay.
Right.
So now people take the like there is a convention that ordinary vectors are column vectors and these
vectors.
functions are row vectors.
Row vectors. I was just thinking when you said that, that's what I was thinking. You were.
Yeah.
Okay.
So we can say functions. Later on, we'll do matrix multiplication and stuff, which will explain the row column distinction and it like it fits naturally with the matrix. But the idea is that if the functions are vectors, then you can create a vector space out of functions alone.
I can guess why, because when you're doing the multiplication, you're doing the row.
Yeah, exactly. So it works like that. You multiply the first row with the first column, right? That's how matrix multiplications are defined.
Yeah, that
so
makes
it
sense.
fits into that. That's why we have done like the functions that row vector.
Makes sense.
But the idea is that because functions have become vectors, linear functions at least, we can create a vector space out of functions.
You can create a vector space out of functions. I agree.
Yes. And that is called the dual space.
That is called the dual space for a vector space for functions of
all the linear functions that you can think of.
Linear functions. Okay.
Okay. So now in pure maths, a lot of areas and some areas of machine learning, dual space is extremely important. When you are solving a problem, so have you heard of support vector machines and stuff?
Yeah, SVM. Yeah, I've heard of
SVM.
that, but that's going to come in class also. I don't know what
Yes,
that.
yeah. So at some point we'll discuss this. And the way the SVM, the core algorithm of SVM is actually solved is you take the problem into dual space and solve it there and come back.
Okay.
Okay. So instead of thinking about vectors themselves, which is what we want to do, we think of their duals. And it turns out solving in the dual is slightly easier. So we solve it there and then come back.
Okay. At a high level,
So
that makes sense. I don't know.
like it's difficult to give too much intuition around
Yeah,
that right now, but
I think I
once you do
understand
that, you will see that dual
why.
space is very important.
Okay, got
So
it.
that's all I'm trying to convey right
Got it.
now. Yeah. So, and then people can do dual of the dual space.
Can you write that there for me as well then too? Just we use dual space for support, just like a note or something. Yeah, used
Yeah.
in support just so that yeah. So SVM. So that when I reference, I know why we were using dual space. Is that's the primary use for the dual space then?
There are other regression kind of stuff where also dual space is very relevant.
Oh, SVM is a regression technique then.
SVM is a kind of regression technique. SVM
Okay,
can do other things also, but SVM can do regression also.
got it.
Yeah. So that's basically the idea behind dual space. Now, linear functional, we had a restriction that it's going from vector to real number. So vector to scalar.
Yes.
Okay. Now let's do vector to vector.
Okay.
Okay. So, and that will give us matrices.
Ah, okay.
Okay. Now, why does it give matrices? Let's think about. So when you do vector to vector, the output, let's say the output is three-dimensional. So that means I have basically three output. Each of those output is a row vector
Vector, right?
because
Row
we know that
vector.
functions
Yes,
are
yes,
row
because
vector.
we're dealing with
So I
functions.
have three rows.
Yes.
So I create a matrix out of three rows.
Makes sense.
So
That
that's
makes
basically
sense.
what the matrix is.
That makes sense.
Okay.
Wait, 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 wait,
Now this,
wait, 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 wait. Why do you have three in the beginning? I lost you in the beginning. Why do you?
because my output is three rows, each row is a row, so the output is three elements. Each output element is a linear functional. So that will have a row vector on its own.
Okay,
So I have to write three rows. So I'll write one below another.
got it.
And that gives me a matrix with three rows and whatever number of columns you need for the vector space.
Got it. Okay.
Okay. So these things are called linear transformations. Okay. So linear algebra, linear function, linear transformation, all are the same things. It only just clarifying to you what the input and output dimensions are. Like when you say linear functional, people will automatically understand that the output is a scalar, not a vector.
Got it.
So output dimension is just one. Linear transformations means the output is also a vector space. So it can have multiple components.
Linear functional versus linear transformations, then does the differentiation.
So basically in a matrix, so each component of output is a linear functional. So, and we put those row vectors one below another and create the matrix.
Got it.
And this is why matrices look like rectangles.
This is why matrices, what? Sorry?
Looks like a rectangle.
Oh, okay, okay, yeah, yeah, yeah.
Okay. So the reason for rectangle is not like something special or anything. It's not like a bunch of numbers we're throwing in around and we want a rectangle to fit in.
Makes sense.
Like there is a natural reason geometrically and mathematically to it.
Yes,
Right?
it doesn't have to be
Like,
a square though, right? Because it
yeah,
doesn't.
it doesn't have to be a square.
Yeah, it can be a rectangle then.
Now, if A is V to V, so a vector space to itself, then it will be a square matrix.
Cool.
Because in general, like the input can be three-dimensional, output can be two-dimensional. So it will be two rows. So three column, two rows and three columns, so two cross three matrix,
Got
that
it.
kind of stuff. But if the input and output is same vector space, then it will be a square matrix because number of dimensions would be same.
Okay.
So number of rows and number of columns of the matrix actually is how many dimensions of the input and how many dimensions of the output. That's what that means. Okay. And
Because your
then
dimensions of your matrix are rows by columns, right? It'll be
yes,
R
yeah,
by
yeah. The
yeah,
conversion is row by columns,
row by
and
column.
number of rows is actually number of outputs
Yes. Remember, rows is number
because
of columns. Yes.
each component of the outputs gives a row.
A row. Yes.
Okay.
Got it.
And then by example, you can have a lot of 2D, 3D matrices. Do I need to write down examples?
I think it makes sense. No, I think I'm good here because we haven't really done any operation. I think when we do
Yeah.
operations,
I will just mention diagonal matrices.
okay.
You know what those are? Diagonal
That's
matrices is
when
basically
the
anything off
first
diagonal is zero.
you, everything underneath is zero. Oh wait,
No, no,
what?
everything above and below is zero. Only the diagonal is zero.
Oh, okay. That's a useful matrix, you're saying?
Yeah, that's extremely useful. That's basically what it is saying is. So let's say I have three dimensions, A, Y, Z, and then I have a diagonal matrix. What does that mean is that in the output, the first coordinate depends only on X. So let's say AX. Second coordinate depends only on Y, let's say BY. And the third coordinate depends on Z, so CZ. So this is basically three functions of X, Y, and Z separated, like the combined, they have no relationship with each other. You
Okay.
can see, right? The first coordinate is just X to AX, so multiply by A. Second coordinate is multiply by B. Third coordinate is multiply by C. You don't need to do any linear combination anymore.
Yes.
Yeah?
Why is that
And then
useful though?
yeah, that's very useful. So we'll write down this matrix as, let me see if I can write a matrix somewhere. There are some matrix.
Oh wow.
Uh, zero, zero.
Microsoft Word is pretty powerful for that.
Yeah, yeah. Microsoft Word can do all of these things. It's just you have to find out and then typing is slow for me. Yeah, this is your diagonal matrix.
I'm seeing it. I'm still confused why that's useful though, today.
That's useful because if you can somehow represent your data in a way such that I have five inputs and five outputs, and they all combine with each other, that is confusing. But if I can clearly tell, okay, this input goes to this output, and the second input goes to second output, and so on, then I don't need a complicated way to explain this thing. Like
Yes.
in
Because
general,
it's not
my first
dependent.
output can be some combination of all the inputs, and second component can be some other combinations, and so on.
Yeah. Then you
If I
have
can have clear separation between, okay, this input only match. So if I change something in the first input, only the first output is going to be affected.
yes.
That's very easy to like handle. Think in terms of like you're designing a system or something,
Yes.
and like you have some targets for each of the outputs, and you know that the first output is only changed by the first input. So you just play around that knob, and like that dial will change only that input. Nothing else gets affected.
Got it. Got it.
Okay. So
That-
this is like the separation of your purpose and all that things.
Got it. This is the
So
diagonal matrix then. Okay.
yes. So that's why these are important matrices. There are other important matrices like rotation. Now, why rotation is a matrix and how to represent them, you may have already seen a little bit. Your
Oh yes, it's like
class, that cos theta, sin theta, minus sin theta, and all those things. Yes.
yeah,
Yeah,
yeah.
yeah.
-1 or something also is there.
Yes, yes,
Okay,
yes.
yeah.
There are more general versions in higher dimensions of those. I don't want to cover now, but if we need in some class, we will do that.
Okay. So
Okay.
Jay, can we pause here today then?
Yeah, sure. We'll pause it.